Afternoon, my name is Andrew Terentjev and I'm CEO of Cambridge Smart Plastics. I'm a banker by training, but I hope you'll indulge me for 20 minutes while I explain soft matter physics to you all. We're opposite end of the spectrum to these guys, so we're a five-man operation, sort of camping in the Cavendish around the corner. So different perspective on everything. But today the focus of the talk will be why we spent probably our entire life as a company focusing on liquid crystal elastomers. Some years intensely, some years not at all. But there are several phenomena with it. It's really a science fiction material. It's very easy to write a paper about it and get into nature. And that's because it does a bunch of really cool stuff. So obviously it's an actuator or an artificial muscle. It can spontaneously, hello sir? Oh, sorry, yeah, so it's an artificial muscle. It can respond to ambient temperature or UV, for example, to change its shape. Its properties are actually largely unique in that it gives it a really spectacular damping or vibration attenuation characteristic. But most recently, and what our company really focuses on now, is it as a reversible adhesive, actually. So a lot of the phenomena before that actually lead to it being very sticky and reversibly so. But what is an LCE? A lot of you will be watching me now on I don't know how many people there are, but some of you will be watching me on a liquid crystal display right now. It's really the same mesogenic units that we're polymerizing into a bulk plastic. So it's the interaction between these sort of stiff molecules which is causing all these phenomena. They tend to align, they want to align, but you can disrupt it. That's a picture of a block of it. And the first phenomena that I would introduce is soft elasticity. So it'll tend to form domains, maybe a micron in scale, where these local alignments will cause it to form a kind of region of purity of itself. And what that means is when you then deform the elastomer, so normally this would stress the network and cause a response, things like that. The LCE will tend to rather keep its domains, but orientate itself in the direction that you're talking about. So that's nicely visualized by somebody up there, where blue is alignment in the plane, red is perpendicular, somebody stretched it, and as you can see, with very low resistance, you actually end up with a transparent. It's usually white because the micron will scatter light, but once you stretch it, it'll become a transparent film in one plane. So that's soft elasticity, and that's resistance-free, which you can see through stress strains. You introduce a little bit of force, and it will, without resistance, stretch, and then turn into a regular elastomer on the tail end of that, which may become relevant to condoms someday. We never found a use for that. I'll circle back to soft elasticity at some point, because actually I find this the worst part of LCE and a limiting factor of it, despite it being what was very popular to write about in the 90s and stuff. The second factor is actuation. So this is the artificial muscle. So this is going to drive all your soft robots and stuff. As you can see at the top, we're using ambient light or turning on a light bulb to do like a muscle exercise up and down. That's driven by introducing heat to the network. So your domain on the right is very comfortable, and that's the dominant force. You introduce some heat. No longer is that the dominant force, but your random walking chains will force a different shape, maybe a sphere. I guess there won't be any domains. It'll just become an elastomer. And so it'll spontaneously change shape into whatever the elastomer would choose to be. And so we made some sort of cool experiments back in the day. We made sort of heat engines, like, you know, the old nitinol hot and cold water things. We did things like that. We tried to do the artificial muscles line, didn't get anywhere with that. To this day, that's really where I think the majority of publications are. These are all stuff I ripped from Nature just in the last year or two, where LCE is sort of principally there. A lot of people are 3D printing it because you align it for free through the nozzle. It's nice and hot. If you align it, then you can control the direction of actuation, therefore make it do cool shapes, things like that. PhD in the group is doing like a braille display, little bubbles that will come up and down with lasers, stuff like that. Soft robots is very popular. I don't get why, but it is. Yeah. So anyway, we spent a long time doing this stuff, and I struggled. I couldn't make a business from that. Nothing really came from the actuation, the muscles and things like that. So we looked at the material again. We had a retrospective and like, what is it actually really good at? Why is it better than other materials? And then there's this tan delta storyline, like, oh, it has a tremendous vibration attenuation potential. What is tan delta? I do know what it is, but difficult to translate into practice, I'll tell you that. This is frequency and temperature dependent, tan delta. It's incredibly broad. When we took that, you'll have to take my word for it, but 0.3 is rubber. So everything above 0.3 is already considered a good damper. So it's excellent. What do I say? Oh, this is a decade old. LC is better than this now, but when people compared it to the status quo, it's better than your hydrogels, your PDMS silicons, which is the most comparable for how it feels and acts. And it was most comparable to, I don't know that word, but it's the substance which is in your joints. So it's the biologically evolved damping system of your body. So LCE was touted as a great damping material. So let's build a business on that. When we took it out there in the world and we quoted these high numbers, they threw back at us, no one's impressed by a ball that doesn't bounce. No one's impressed by XYZ. We've seen higher tan deltas. That's a random Japanese polymer where I think I consider it cheating, but they've got a block copolymer where they've aligned all the glass transitions to make a spike in tan delta. So it's incredibly dampy at ideal conditions once a year. It will melt at high temperature. So it's not really comparing like we like, but just throwing tan delta into the world didn't impress anybody. Yeah. Then what did we do? We tried to make the crash helmets. We thought damping, paratrooper jumps out of an aeroplane with shoes, lands, I can start running straight away. We did, yeah, we'll come to why that's dumb in a minute. We did our Hopkinson bar tests. You shoot a ball out at incredible speeds. Nothing gets through it. You see the silicon has a resonance. We're overdamped. Q factor below 1 means overdamped, so nothing gets through. You drop a ball on it, you get local heat, doesn't bounce, etc. All very attractive until we again went to market and very quickly realized that in the car example, it's going to be the momentum transfer which kills you, and actually impact as a whole field is rather about spreading force over time rather than whether you can have a silent impact, and no one's going to care that your bumper became incredibly hot and there was no kinetic energy left over in your crash when actually you've flown through the front of it or something. So yeah, so your paratrooper is still a pancake despite silently being so. So all we got from that line of work was a cute paper about momentum where the top little curve is your Newton's cradle thing, where it's two equal masses, elastic collision thing. So you maximally could damp 50% there. So you would have the ball come in complete pure silence. The two of them would move on together the other direction, but at half velocity. So you can map that, so whatever. That doesn't help me make a business either. But vibrations, shear waves through surfaces, etc. Fear not. Shooting a laser on top and shaking it from the bottom, we can prove again that LC is an excellent vibration damper. So silicon has its own resonance, and then the metal contraption has its own resonance. LCE nicely spreads that out, reduces it a lot. So there was hope, and I still think there is hope, and this is where modelers will someday help us, perhaps. Because as I got into the vibration space, I saw that it's actually very much an engineering or compound problem. If you think about acoustic foams, for example, they're scattering through different materials. They're using air and cells to really change the directions and the speeds of all these waves. Equally, if you don't know about acoustic black holes, read about them. It was quite interesting. You can have a piece of metal which dampens itself because you sort of turn them on themselves. They cancel out, or God knows what. So there's an enormous amount of, I guess I want to say, engineering or bespoke nature to every solution. The resonance of this table is different, so the perfect solution isn't whacking some LCE into it, but it's going to be possibly cheaper if you make a spring or something, or both, I don't know what. But every solution was therefore unique. Every problem required a different set of materials. And so it's not scalable for us. It's not like we can just start making LCE and everyone's riding off into sunset. So I do think this is fertile territory for you mathematicians out there. These are just papers this year from Bhattacharya and Gorelli. These are not damping. He's looking at why this Hertz indentation. So you push a ball into it and it's a very unusual response because of soft elasticity. And the same where are you harvesting your polymer from when it's actuating. So that's just the beginning of it. If you guys were to look into this vibration attenuation stuff, I think there's probably an enormous amount of mathematics and modeling to be done there. What we actually do though today, probably, because I still think we'll do damping someday, but what we do mostly today is the adhesive tapes line. So this was kind of anecdotally known always. If you have LC on the bench and you accidentally put the samples on top of each other, good luck separating them. And so, I mean, this is also like an example. I brought a sample with me, and it's just completely laminated itself to the metal by accident. So it's a very sticky substance, and that actually does come from the damping. So again, naively, the banker again, not the expert, but I thought it was going to be about surface energy. I thought it was going to be about mechanical interlocking. I thought that's what adhesion is all about. But actually, it turns out damping is the, by order of magnitude, most important factor in how sticky your pressure-sensitive adhesives are. Because it distributes it nicely through the network, it shares out all that force and dissipates it into heat. And you can see that kind of evidence by the different cross-linking density reducing the peel force of our LCEs. And I mean, there's been a lot of like research and like thinking about that lately, and this is the soft elasticity at work again at the bottom. Actually, when it delaminates, if you look very closely, it's transparent in the surface. So as we're pulling it, you do cause the alignment on the surface of the domains, which then restricts it, kills your damping, boom, let's go. And we did change the chemistry a few times because some other field of hot melts taught us that dangling chains like to lie down and anchor themselves, etc. So we added side chains, all sorts. None of them ever really improved it because they do their own stuff. They slap the surface and prevent the LC working, I don't know. But LC always worked when it was maximally damping. And that's also why heat kills that, because when you heat it up, it's an isotropic rubber, no more tan delta, and so it lets go completely. So anyway, that's the kind of stuff we're working on now. What do I think the success factors are? We're not yet successful, but what did I learn so far? I'd say, is it actually pushing the material itself is pointless, no matter how cool it is. Nobody buys the material. They want a widget, they want a product, and that product must be made of something. And if you're better, then sure, you'll enter the market, but you first need to have the widget. So when I look to our competitors over in the States, Mr. Yakaki has a startup over there who does helmets. He did do the impact damping thing, and with more money and time than us. And what happens there, they do seem to be working, but they make a polyurethane diamond lattice where they've stuck LCE into like tiny little nuggets in it. So it's not really LCE anymore, it's a polyurethane collapsing lattice, things like that. But the point is they've had to choose a widget and then push that. So material science, unfortunately, is difficult business, and you can't just invent something cool and then expect it to sell. You need to first find a problem, find a product that requires your material. That's why, for example, I think this actuation stuff is too left field. Like it doesn't really exist. There isn't a need for it. There isn't like a problem that I could find where you needed an artificial muscle which will act differently when a sunny day is there and when the UV is different and stuff like that. The other thing I learned is that if there's an engineered or a solution or a compound solution, then it's really hard. And again, the material won't sell itself. Then again, focus on the product, focus on the model, on the optimization. Every time we entered a market where you needed a complex thing, LCE suddenly fell away in terms of how good it is because you could achieve it cheaper somewhere else or buy a larger object, something like that. But fortunately with the adhesives thing, we did find enough trends, enough market push, things like that, pull problems. For example, there's a right to repair bill, like your iPhone is structurally bonded together, so you can't repair it. You could introduce screws again, but they don't want to do that because it's fiddly and it's heavier and things like that. So a reversible bonding tape, fantastic. You can sort of UV or heat and pop open phones, things like that. And sustainability is also there because all tapes sort of by definition are single use, and here you could have it endlessly reused. Not true because dust and skin will spoil it, but you can always wash it in solvents and it'll go back to work. Then other things we learned are more like the practicalities of material once you leave the lab or leave the academic lab. First thing we discovered is that smell and color are not tolerated. So we also use sulfur in everything because of chemistry and how robust it is. Everything reacts, blah, blah, blah. We had to immediately remove thiols and sulfur and things like that because every time we spoke to a company, no one wanted to deal with us anymore because even if it's fully reacted and it doesn't smell anymore, the fact that you might heat it someday and then your sunglasses will have a little whiff of sulfur was intolerable to them. And then again, we use amines, they go yellow, so God help us, we have to add things, get rid of the yellowing and things like that. So the chemistries had to change substantially to the detriment of the product for it to become industrially relevant anyway. And then, of course, there's the cost factor, which I think will still be why LC doesn't succeed in the near future. I was tens of thousands in the 90s, or priceless because you had to build it yourself. Since all the patents lapsed, you can buy bad quality stuff from China at $500 a kilogram. So what I did know more from we have a biopolymers line as well, but more from that, what I discovered is that everyone will pay you and will say they want your research, and they'll follow it all the way through until they realize it doesn't cost less. And despite the fact that it's environmentally friendly, despite the fact that it's maybe better at its job, if the cost isn't at least the same, then they always sort of drop the project or say like, great, we'll keep it on file, et cetera, et cetera, et cetera. And so LC requires that first breakthrough product so that it reduces in price, so that people actually make it in bulk, reduce the price, find something efficient to do with it. And as it reduces in price, as people play with it in the market and people become more educated about it, the real people who make products will start to think of the ingenious things you could do if there was an actuator, embedded in something. And then it will become the material we all use and all know about. Got to do an end slide. Okay, cool. There is something. So that's my speech. Yeah. So thank you. Yeah. Oh, I nervously spoke too fast. Yes.
The adhesive. So,
yeah.
How does it work? If it does have something to do with soft plasticity, which seems non-obvious.
Yeah.
How? Sorry, not soft plasticity. With the
damping.
The damping.
Yeah.
Which doesn't seem like an obvious thing. Does that mean that it's got a strong frequency or rate? Is it only adhesive with respect to trying to peel it up quickly, for example?
No, so that reminds me of non-Newtonian stuff. No, it's always sticky, regardless of how quickly you're pulling it. I guess we've never tried actually a study on the speed of it. I understand the damping comes from these mesogens having kind of a friction. As they move past each other, they break and reform bonds, and et cetera, and the domains at the same time also move past each other and interact with each other. So that's where all this friction and heat is being generated. What was your question more specifically? I haven't studied rate dependency of how fast you pull it off. Why we think it's sticky is because that's the only thing that's unique about it, and it's sticky. And we met with sticky experts of the world, and there are two camps in the world. The majority think it's surface energy and stuff like that, and interlocking. And there is this rebel group, Steve Abbott, whatever his name is, and some other guy. And they are of the school who believe that it's damping. So we have academic supporters. And because it's so sticky, and reversibly so, because what changes when you heat it up? All you do is you remove the liquid crystalline element of it. And why is it then not sticky at 80 degrees? Yeah, so we do think that there is a reason to believe that it's the damping, which is the stickiness.
I mean, there's a distinction between adhesion and tack.
Yeah.
There's a connection to the rheology.
I mean, this is a PSA, or is it more on tack and stuff? I think that's kind of like we'll talk about it. So it's not some structural epoxy style bond.
But the damping theory, the TGM at least said stuff.
That sounds, yeah. They're very
bad pedigree.
Yeah, look the micro.
Sorry?
Look the
micro.
Yeah. Vitrumers guy. I don't like Vitrumers. Don't believe in them. Yeah.
Leave that in.
No, like, we tried a lot on Vitrumers.
James.
Thanks for that, very entertaining. I also had a question on the adhesion. He does work on grafted polypropylene sticking to metals, and there, the stiffness of the polymer close to the does influence the strength quite a lot. I wondered whether there might be a stiffness effect of the orientation, maybe stopping, pulling off individual ones one by one, and maybe then you switch from the peel mode to having to pull the whole thing off all at once.
That's good. So you mean that it's because it's soft or dampy, it distributes it, and the whole thing is resisting the peel?
It's a bit like if you try and pull it off, it's easier to pull it one rock at a time rather than trying to pull
Yeah, 100%. I think that's why. That's also why I think we went down the line of these dangling chains. We thought if we added these dangling side chains, it would increase things, but maybe the length was wrong. But every time we did that, all we did is dilute the liquid crystal mesogen element, and it got worse. So in the end, our best performers are really the old ones, where it's really like just a lot of mesogens and a simple spacer.
Do they change their stiffness a lot when you go through this transition?
I don't have that in mind. I don't think so. It really feels like a sort of PDMS rubber. So yeah, I don't. Sorry, I can't. We did do a project where we did covalent bonding because we did some paper by Wolf inspired us, and we did some sort of covalent cross-linking. And I do know that, I think to your stiffness point, where it's the entire plane bonded, it's only one plane which breaks. And we made a very good welding thing with vitromers. Actually, you can weld vitromer plastics because they bond exchange, and it becomes, to me, a three-dimensional bond. And every time we functionalized a surface and bonded it, it was incredibly brittle because you only have one plane, and so the crack propagation is very pleasant. So that would be my 5 cents to the direction that you're working in.
Thanks for the talk. It seems wonderful the way that you have zeroed in some application with these kind of reversible adhesion. And I was wondering, could you share what is the current challenges? Because if it really works, I mean, let's say all the bond is not just different all bonds, all kinds of things.
Yeah, everything.
For assembling sustainability.
Yeah.
What are some challenges that you?
I mean, a little bit touched on it. Cost is a hidden challenge because with that application, that hasn't reared its head yet. They say keep going until we find out. It's very, very good, and there'll always be some high-value application you can maybe think about. The challenge was changing the chemistry substantially. And then there's this sort of, I guess, the secrecy of the companies. They don't want to tell you what it's going to be for and things like that. So to build a relationship there, I think those are principally it. So changing the chemistry was horrible. That set us back a lot in changing properties. Yeah, I mean, the challenge is the cost, yeah. That's why I think it will die in the end, or it might die. Yeah.
Questions?
No. It was a pleasure.
Something to me sounds like guessing Bob's story about how to try to exploit the material.
Yeah.
It's told us here, but you consider maybe writing it up.
Writing it up?
Yeah.
Like a book?
Yeah.
Did you get to buy it? Yeah. Yeah.
Or meetings.
I think so, because I mean, I didn't go into very much detail because I don't want to, I can't tell you most of the things, but yeah, no, it was a good journey. If you think about it, yeah, maybe let's chat in the coffee break. Yeah. I think first it must become a success, and then I can retrospectively write about it. Otherwise, it's the musing of somebody struggling like against the world. I guess that would appeal in its own way, but yeah. Yeah. That's the story of CSP, yeah.
Okay.
Yeah.